Welcome to the virtual presentation of All-in-One Print, designing and 3D printing dynamic objects using kinetic mechanism without assembly. I am Jiaji Li, and I will be presenting our team from International Design Institute of Zhejiang University. All-in-One Print is a design tool that allows users to redesign any solid models into dynamic 3D objects. The main contribution is that all these kinetic motions and components could be one-step printed without any assembly. For a conventional print assembly method, making such a kinetic model could be pretty challenging. It requires 14 hours to print all these 18 components separately and another hour of manual effort, including support removing, surface polishing for glue, and pretty a while of assembly all these things together in strict sequence. By taking advantages of articulated structures made with SAS printer, pump-up print with biomaterial, and of course metamaterial, bridges printing, and the idea of remodeling design tools, we introduced the all-in-one print method, which fabricate all these components together with one step, one cycle print within 5 hours. As the video shows, the kinetic mechanism performed pretty well with a stretchable body and two rotatable arms. Let's make a comparison with a familiar case, an articulated snake. We can see all the snake components are attaching to the platform. They are flat arranged to ensure the flexibility. And its motion are quite uncontrollable. For example, if you lift it up, it droops down like a dead snake. It also needs quite a lot of effort to make all the specific designs like slug, shark, and swarm. So, in contrast, our method enables spatial arrangement, which means the component could be arranged upon the others. It enables controllable and linked motions for more complicated use. Of course, as a HCI research, we also build up with a design tool for infinite designs of such structure. So how did we enable it with the most common FDM 3D printing? Let's start with two unique printing strategies we use, arc printing and support bridges. Drooping is a common problem happens in 3D printing, especially for relatively long bridges. For two components with slight motion, like figure A3, this error will definitely make this motion disabled. Our method change the path of the nozzle to be slightly archy, which fix the error caused by gravity and make this component work pretty well. For a 10 centimeters long bridges, conventional method would be drooped badly, but our method would make the bottom super flat. We control the printing path with arc fitting algorithm of arctangent function. In the first layer of arc printing, the arc rise is pretty high, but after that, the heated nozzle would work like an iron to flatten it. After 3 or 4 layers, it would be totally flat and it could be printed in conventional way. Here is the result of our experiment with all of former parameters controlled. Our second method is called support bridges. For two components at left as example, the conventional method would generate support in between, which could be hardly removed even with tool. Our method would generate those two tiny filaments to replace the conventional solid supports, and they can be easily torn off with even bare hands. For the component not attaching to the platform, our method would automatically generate support bridges to support them. according to the size and the load of it. Our experiment shows that the bridges could be easily broken with the strength of lifting up an apple. With our printing strategies, we can easily fabricate motions of rotation, slide, screw. These are all of 1 degree freedom motion, which could be used for further complicated motion. We also designed some specific structures to help the components to be multi-stable, like the rotate motion could be stable of every 60 degree, or 90 degree, or 120 degree, and the slide motion could be stable of every certain distance. With the combination of slide motion and rotate motion, we can produce a box of only half hand size, and it could be stretched to a person's height. We also built up a design tool for users without expert knowledge of kinetic mechanism and modeling. I will take a turtle as an example to introduce our workflow. Firstly, a solid virtual model is imported. Then users can adjust the remodeling position, the kind of motions, and the size of gaps to get their ideal results. We can see the final result has a stretchable head and tails and 4 rotatable foots. Let's look into the applications of all-in-one print to see what we can really do with our method. We modified a jellyfish with 6 tentacles printed inside it. It has a loose and sagging kinetic motions that allows the tentacles to swing with the manual movement or even gentle wind. For the hedgehog, we enabled 22 rotatable spikes and designed the connection part to achieve the linkage of the mechanism. As the behavior of a hedgehog when it is frightened, the slide motion of its body allows its head to retract, with all spines standing up in a defensive stance. We have also combined the screw and the rotate motion into a single integrated printing as a lipstick. This device converts the user's motion of rotation the body into lifting of the crane container. The lifting motion is smooth, and the final state could be maintained with 25 degrees of over-rotation. We also fabricated a MIDI keyboard as another example of all-in-one printed interfaces. As the final application, Strandbeast is a famous walking kinetic sculpture. Printing it using the all-in-one print method not only eliminates the need for assembly of hundreds of linked components, but also significantly reduces the time. The placement and the density of support bridges are generated based on the weight and the geometry of supported structure. As future work, we plan to integrate all-in-one print with slicing software for wider democratic manufacture. We are also looking forward to use all-in-one print concept in robotic, fashion design, and aerospace industry. Thank you for watching.